next technical report from BIT. The presenter is Xinmei Su.
Okay. Hello, everyone. I'm Xinmei Su from Beijing Institute of Technology, and this is our system description for BIT SR system. It's the overview of our system description. We have 5 parts. The first one is the related work is based on the baseline system Ikapa TDNN, and our improvements have 3 parts. The first one is the multi-scale convolution layers to replace the single-scale convolution layers. And the second one is we add more skip connections to avoid overfitting. And the third one is the combination of multiple poolings. Okay, let's see the first part of our proposed system is the multi-scale convolutions. We adopt 2 layers of convolutions. The first one, in the first layer, it has the kernel size of 5, 7, 3 respectively. And after each layer of convolutions, we have a concatenation along the channel steps. And the second part of our improvements is the residual blocks, just like the ResNet. We use it because we use more skip connections because when training, we found that some overfitting problems. So we think that the skip connections can solve these problems effectively. And the third one is the combination of multiple poolings. We use not only attentive statistic poolings, but also the SPOC poolings. SPOC poolings is a very famous pooling in the field of image retrieval. So we also adopt it in the speaker retrieval tasks. It's just like the mean average poolings, but we also adopt a fully connected layer and one-dimensional batch normalization layers represent as follows. And after these 3 steps, we adopt the experiments. The data set we use for training is the CNCLab 1, 2, and AI shell, except CNCLab E. And the dev and test set is the SR dev and SR test sets provided by the organizers. Okay, let's see the acoustic features. We use the 3 seconds of fixed length chunks, and the input features is the 80-dimensional mel filter banks. No VAD is applied during training, and 3 augmentation recipes we use is the spec augment speed perturbations and adding noise and reverberations. The training settings we adopt all these tests in the SpeechBrain platform with PyTorch framework, and the speaker embeddings we extracted is the 192-dimensional vectors. In the first 20 epochs, we use the Atom optimizer, and the learning rate is set to E2-5 on CNCLab 1 dataset, except CNCLab E. And in the following 20 epochs, we use the fine-tuning method, and we adjust the learning rate to E2-6 on both CNCLab 1, 2, and AI shell. And the margin and the scale parameters to compute the AM loss is set to 0.2 and 30. Okay, it's the results of our proposed system. You can see the baseline system achieved 0.726 and 0.5773, and our proposed systems outperforms the baseline systems. It increased to 0.868 and 0.7085. And we also adopt the ablation study. We removed the residual blocks in the SC residue blocks, and it dropped slightly. But if we remove the multiple combinations of poolings, just use the statistic attentive poolings, it drops a lot. You can see that it only achieves 0.8484 and 0.6439. And we also replace the multi-scale convolutions to the single-scale one-layer TDNN. It also drops little. And And one may argue that in the multi-scale convolution layers, we use 2 layers of convolutions. It may be better than the baseline system because the baseline TDNN is just 1 layer. So we also use the ECAPA 2-layer TDNN to adopt an experiment, and you can see that it can outperform our system. Okay, we also adopt a qualitative analysis. And in the left is the baseline systems clusters, and on the right is our proposed systems. You can see that in this picture, our proposed system can better compact intra-speakers and separate inter-speakers, so our system can do more effectively. Okay, finally is the conclusions to our systems. We have 3 steps we take in our system is effective. The first one is the multi-scale convolution layers applied to substitute the single-scale TDN layers. And the second one is the residual layers in SE-REST2 blocks. It can better solve the degenerate problems in deep networks. And the third one is the concatenating of the SPOC and statistic attentive poolings. It can provide more spatial information than single-scale poolings. And all steps of our enhancements achieve better performances compared to the kappa TDN baseline system. That's all. Thanks.
Thank you very much, Xinmei. Let's see if any questions from our audience. First of all, did you check if the improvement can boost the performance on speaker verification rather than the speaker retrieval?
We didn't do the speaker verification task because the time costs.
You didn't
So
register for that?
Yes, we didn't register the speaker verification task. We only participate in the speaker retrieval tasks.
Okay. Yeah, I'm a little bit curious because you see, the previous team has reported many fusion systems, but you didn't do that. Did you try the fusion, or you just found it doesn't work?
Yes, we try fusions, but it's strange that in the speaker retrieval tasks it doesn't work because maybe retrieval we only select top 10 from a large data pool, so maybe fusion is not really effective.
This is a quite interesting message. Because you're the number 1 in such task, you must have many feeling what makes things better and what cannot. So from you, what do you think the important thing for speaker retrieval? But because this is a new task for us, we didn't have much experience on that as well. What's the most important thing for retrieval from your view?
I think that is the precision of selecting from a large data pool, and it really costs a lot computational complex.
Okay.
Yes.
Okay. So this is why Professor Lee said that we will measure the speed and the computation cost next time.
Because when the coding we use maybe for 1 day or 2 days is a long time.
Okay, 1 or 2 days. Okay.
Yes.
All right, nice. yeah, if no other questions, thank you, Xinmei, for the participation, and congratulations again to Tim for the
Okay.
great achievement.
Okay,
Thank you very
thanks
much.
very much.